continue on this introducing the spring element. For the second example, if we have an elastic support, something like this, and these are simply supported. So if we have a loading applied to here, let me call that is P, and we want to get an equilibrium, equivalent spring constant KEQ. And so say such that this is the displacement degree of freedom we measured. Okay, so that is the degree of freedom we measured here. So we want to express such an equivalent description of the spring for such a simply supported beam. So from mechanics material, we have a way to calculate the diffraction at this here. So we have a way to describe the diffraction, and that diffraction is given by delta equal to PL3 divided by 48 EI PL3. Okay, and here we only concern is the amount and the downward. So here is a sign, negative sign, meaning that's downward. But if we only take the magnitude, that is this one. So again, by KEQ, that definition is the force we applied divided by the amount is deformed. So that's the KEQ. And using this relation, if you manipulate this equation, P over delta basically will be equal to 48 EI and divided by LQ. So that is the equivalent spring constant for such a the simply supported systems. You okay? So yeah, again, using the slides will save us a little bit time in the way I can give you more. And usually before I've been teaching, writing on whiteboard is really slow, and so in this way, hopefully, if you have a print, and you can make the print something like this, yeah. And my suggestion, this could be too small.
Yeah.
Yeah. In my original design is this, and I wish that your notes directly right onto these slides, finding the space around. And that's my original design. So I think the slides I uploaded is the one page, right? And I put the page in the middle. Somehow the PowerPoint slide won't allow me to shift that single page to the top. Otherwise, I just try to save you more kind of empty space around that kind of slides for you to take notes. And that's the best way. On the other side, if you are a very quick note taker, I'm not, okay. So you can quickly just write down draw the pictures and then write the notes on your notebook. That'll be another way to do it, okay. But sometimes you might lack of time to complete everything. So maybe the good exercise from chapter 1, you can try the couple ways to see how can you adapt to these things, okay. And I have all the slides. I think in this semester I will try using this kind of mixing way, because that really is more systematic and then can save me a lot of time on the whiteboard. If you are very good candidate, the electronics, the candidate, good in that way, maybe you can have some way you can write it directly on the board. Okay, so that is, here we stop for this one. So basically the same idea, we can repeatedly apply to any other system. And those ones, again, from the mechanics material and book, you should have other more examples really depends on the applications. Okay, now we come to a little bit more relevant information to this class. So if we have a multiple springs, and the spring can be connected in a couple ways. The first connection method is we call the parallel connection. The parallel connection is the configuration like this, okay? And how can we find the equivalent spring constant? So the description mathematically is this. So we have a K1, K2 connected through a rigid plate. So this is a rigid and no mass. So that's basically, this is simply a notation for connecting the two springs together in the parallel way. Okay, so that means we're assuming these are rigid. That means no additional elastic constant will be considered from here. We consider this plate as no mass. That means this plate contributing nothing to our vibration analysis of our vibrations. Okay, so that is the notation for this. So now the combination of the two springs, in this way we want to get equivalent. The K here is the equivalent spring constant. The result simply is the summation of the two springs, and how that is. So here I can give you a little bit more the explanations. So here, say this is a force half, the force here. So that's a K1, this is a K2 here. And this one we want to have an equivalent spring constant. So let me using the same notation K. So again, this is the force applied to here. Okay. So in our understanding, the spring will respond to force by deforming. So assuming the spring will be deformed from here to here, so that is our delta. Let me take that the delta. Delta is any dummy distance, we simply take it for analysis. So delta from Hooke's law we know is F divided by K. Okay, or simply equivalent is F equal to K times delta. Again, K is the equivalent spring constant. So the two systems must be equal. Okay, equivalent. That means under the same situation, we take the same node. So that means this location where the force applied is going to displace by the same amount of distance, and we call the delta. Okay. And by doing so, then we can see we're doing the free body diagram. So under these situations, I take the free body diagram of this plate. So this is the no mass and rigid. So that's the free body diagram. On here, you can see this is the F we applied. The reactions from that produced from the spring, that is because right now under this situation, the spring has been stretched. So it's going to produce the recovering force going back. So the going back, that means going back to his original shape. So that means that is the direction of the spring force applied to this plate, going back, try to push, and not to try to get this plate back to his original locations where the spring is undeformed, right? Okay, so in this case, the magnitude equal to K1 times delta. Similar way, the second spring, that is a K2 times delta. Okay, and everything under here is an equilibrium status. So by force equilibrium, F equal to K1 plus K2 delta. So under this case, from that information, F will be equal to K1 plus K2 delta. So from this, you can compare K is simply equal to this one. And that's the reason. Okay. So keep in mind, the features of the two springs, they are in parallel connection, is such that the two springs deform at the same amount. That is the major characteristic for people to distinguish the spring or in parallel the connections. And again, the major features is these. The two springs will deform at the same amount. Okay, keep this in mind. And with that one, you can see, we'll look at this example here. Tell me, again, this is a rigid and no mass. That's simply a connection symbols to combine the two elastic bar. Okay, so elastic bar, again, this is a side note. So if we have an elastic bar and this has a Young's modulus and cross-sectional area and have a length L, under the loading F, so this one, this end, due to the application of the loading, will be deformed by delta. And again, a couple of days ago, we have seen the delta equal to FL over EA. So that means F divided by delta, by definition, is our K, spring constant KEQ, and that is F divided by delta EA over L. F divided by, yes. Okay, so this is a spring constant. So here I use the notation K1. K1, that is spring constant for this elastic bar. Actually, most explicit have this one. If we know the Young's modulus, if we know the geometry and dimensions, you should know the K. You can calculate K. Okay. So here for this example, we're using the two different bars for connection like this. So this is a clamp, this clamp. Tell me whether the two springs, the two equivalent elastic objects, the spring are in parallel connections or not. They are.
To deform, the other one has to deform.
Because they deform the same amount. Okay, take it. Okay. Although you look at this one in terms of the drawing, they are in parallel, but you stick with this notation here. The parallel connections, they must have the same deformations. And that this example fit into that definition exactly. So don't be treated by your eyes. Okay? You good? Think about this. And the next one is the spring in serial connections. And for this case, the two springs connected in this way, and then the equivalent spring constant will be formulated by this. That K is a spring equivalent spring constant. Then we can again repeat this similar analysis by taking a free body diagram. So let me redraw this one here. So this is K1, this is K2. And here I use the dot simply to distinguish the portion of each string. Okay. So this one is on the loading. How about let me use the different colors for loading. So this is the loading F. Okay. And this one we have an equivalent spring the descriptions. So we want to describe by this KEQ. For that one, I'm using K. Okay, so I stick with my notations K. And again, this one is under the same magnitude of the loading. Okay, so we want to find K. So again, from here, for our analysis, we assume due to application of the loading, the spring deformed at where the loading applied. At where loading applied, we assume that deformation is delta. So by Hooke's law, F equal to K times delta, or simply K equal to F divided by delta. Okay. So that is the very straightforward from here. And now we using the same loading, using the same deformation, and again. We describe the equivalent system is such that the two systems, if they are equivalent, their loading must be the same. Their deformation must be the same. That is what we call the equivalent system. Okay, so under these situations, at this end, they have the same deformations. So that's called the delta. Okay. Now we take the free body diagram here. So this delta is the total deformation contributed by the deformation of this and this, right? So right now we take the free body diagram on the individual springs separately. So for the spring 1, so this is a K1, and then this is a spring 2. So this is K2. Okay. So now we take the free body diagram on the individual springs. So you see, this is the application of the loading due to action reactions or due to force equilibrium. What is the magnitude of the force here at the end, F, right? And on the opposite directions. And this point, on the free body they are same points. So that means on this system they are action and reaction. So this is the magnitude of force. Again, the force transmitted to here, that is the magnitude of the force. Okay? We good? So now we begin to write. So the deformation of the first spring basically is the force it is taken divided by his spring constant. So this is the amount of the deformations on this spring. The deformations of the second spring is this. Because the two springs they connected in this way, so their deformation will be accumulated in total equal to this. Are we good? Okay. Any questions about this? This is the key. Okay. If no questions, then we can proceed. So by here you can see delta, or either way I can rewrite one more, delta equal to F over K. Okay, simply, I think this is not important. I want to use this one. So I use this information to here, delta equal to F divided by over K. Divided by K. So in this way you can see 1 over K equal to 1 over K1 plus 1 over K2. And that is this equation here. Okay, good. So anyone of you can tell me what is the major features of the spring connection in series? Yes.
The displacements are different, but the loadings.
Loading the same. Okay, good. So the loading is the same. So taking this feature to justify whether that spring the connection system is in parallel or in serial. Okay. So in serial connections, again, the feature is such that each component of the spring, they taking the same amount of the force. The force simply translated through seriously through kind of the kind of spring the spring systems. And here I emphasize the features of the series or the parallel connection is many times the connection of the spring will be the mixing of the parallel and the series connection. So that moment we do need such kind of techniques to do the calculation kind of the level by level. Okay, and we'll see. Before we proceed, and here I modified the previous example a little bit, but this into this. So these are two the same elastic bar, okay, and this clamp on one side, and right now the rigid is here, the force applied to here, okay, the force right now is applied on the rigid bar. So in this way you can see once we apply the force will be transmitted to this bar. In turn also will be transmitted to this bar. The force on each bar are the same. So basically such a configuration is in serial connections. Okay, good. So we can try this example here. So this example is such that arrangement is this. Let me explain. We have a loading. The loading basically is through a weight of a block. So basically the force here is simply equal to W. Okay, so this system is such that it's going to carry some loading. So basically loading applied at this end. Okay, and this end is kind of the part of this. This is kind of the wire, and that is elastic wire. Okay, so elastic wire basically have a length L, and then you assume it has a Young's modulus E. It has a cross-sectional area A, and through this wire connected here and through this pulley, and assuming the pulley has no mass and rigid, basically contributing nothing to our analysis, simply is a force transmitters. That's it. And this whole system sitting at the free end of a cantilever beam, and which is elastic. So basically, in this system, we have two elastic portions. One is this, and one is this. And here we want to calculate what is the equivalent spring constant of KEQ in terms of the material properties and dimension. And here I'm going to describe this to you. So let me work on this example quickly. So I'm going to put more symbols on here. So say this is elastic, and it has a Young's modulus, say E, and it has a cross-sectional area A, and it has a length L from here to here. Okay, and again, this is elastic, and it has, let me assume for simplicity, has the same Young's modulus, has the and the moment of inertia, and has the length L. This length is what is that length? That is B. Okay. So this length is B. So for this case, you can see the first one we can come up with the this is the loading here. Okay. So basically this representing the loading. So the first one we need to tell whether this system is in the series the connection or in parallel connections, because the different cases have a different I would say formula, right? So that's the first step. So which one? Series? Why? Yes, the answer is yes.
Because both the forces transmitted through both equal.
Good. And you can see this one quickly, and we can do it using the drawing the free body diagram, and that will help us to verify. And free body diagram apply to the elastic portion. Okay, so the free body diagram, first one I want to draw the free body diagram is on this one. So here, this is this portion. Let me call this portion 1, then this the portion 2. Okay, so here is the loading we applied F here, and due to action reaction, this is the force here. Okay, and now I draw the free body diagram on the second portions. For the second portions, you can see this force somehow is kind of transmitted around the wire and then to the pin of the pulley, and then trans down to the base of this kind of pulley support. So it's a little bit more complicated, but equivalent here, roughly, you can say this force actually is equivalent to this one, action reaction, right? Okay, so now you can see this is an elastic object 1. They have the same force as the elastic object 2. So this system is classified as the spring in series connections, in serial connections. Okay, so now we can do this one. So that one, from here you can pretty much easily to formulate this is the spring K for system 1, and that is spring K for system 2, and then or 2-1 other way, either way. Okay, so let me do this one, and then this is our force. And what is 1? 1 you can turn over your slides a little bit earlier. The K1, this is the elastic bar, so the K1 equal to delta equal to FL over EA, F divided by delta, EA divided by L. Okay. And KQ is the cantilever beam diffraction with this one. So that one, I forgot the formula, I need to turn over. 3EI divided by length cube, so that is this one. So therefore, in this case, this equivalent system will be equal to this. So we know the K, let me write it up here. So KEQ will be equal to 1 over K1 plus 1 over K2. So that is our equations we just come up with there. questions? Good. Okay. Good. If no other questions, and I want to move on to here. So now for these examples, I want to demonstrate a little bit the other applications of calculating the spring. So basically, this kind of the system is nothing regarding, a little bit different. Okay, basically it's the connection of the spring through a level. Okay, level, that means that is a rigid, no mass, and basically level is kind of, you can tilt it in any orientations. Somehow the spring connected to that level, okay? So under this case, how can we calculate the spring equivalent to, for example, I want to assign my equivalent spring at the free end. Okay, then we see this scenario, we see how that goes. So basically here, assuming this is the rigid, that means the tilting always remain as a straight line. Okay, this part, this level always remain as a straight line during the tilting. Okay, so that means this is original status, this is the final displaced the status. So that means these two lines are straight line. Under these situations, basically the portions of displacement YA, YB, and YC here, they remain in the proportionality. The proportionality is regarding is related to the distance where the spring locates. So that is the features we're going to use. Okay, so under these situations, you can see there's two ways we can find the description of the KEQ. The first way is with using the conservation of the whole strain energy. The equivalent systems deform such that its equivalent strain energy must be equal to the original one. We're using this principle. Okay, so that means the total is the spring constant, the strain energy stored in the spring is stored in a spring is such that, so say this is the deformations. Let me call the X, okay? So this is the force. By Hooke's law, we know that it's in linear relationship, F equal to Kx, right? So this is the slope equal to K. So the more you stretch, the more energy you store. So for example, say if you usually the strain energy is described by the area underneath of the strain line, okay, under the curve. So for example, if you stretch the spring to any arbitrary position, then that position be parametric. So basically this area is equal to how much? 1/2 of this triangle, the area that is the base multiplied with height. What is base? Base is x. What is height? Height equal to f. F equal to kx. So in general, the strain energy is equal to kx squared. Okay, so using that parameter here. So for this case, assuming this level is deformed by that much, the spring, the energy is equal to KEQ times the deformation square. The deformation, assuming here this one is deformed by that much, and let me call it YL using my notation here. Okay. So if this deformed by YL, so say this is a YL. Okay, because again, for the equivalent system, they under the same loading, under the same deformation, we have the same setting. So the total strain energy must be equal on the two systems. For this system, the strain energy is stored in springs. How many springs? We have two springs. So there's a two terms of the strain energy described here, right? One is from this spring, the first spring. So one half times Ka times deformation square. What is its deformation of this spring? Again, you look at this one, and that is Ya, right? And here, let me do a little bit more. What is Ya? Ya, due to the proportionality, equal to YL times A divided by L, right? You good? Okay, so that is A divided by L times YL. The same thing for the second spring, that is 1/2 and spring constant, and multiply its deformation square. The deformation is equal to YB here. And what is YB? YB can be related to YL is equal to B divided by L. So this is B over L times YL. Okay, so you look at this carefully. On the both sides of this sign, the equal sign, we have YL. We can eliminate these constant terms here. So in this case, can you see the KEQ will be equal to KA times A over L squared plus KB, B over L squared. This is not formula, this is the result. You don't need to memorize this formula. This is simply a calculation result. Any questions?
I have one question.
Yes.
You might have said this, but I missed it. So how exactly, I'm confused about that A over L relation between YA and
Yeah.
YE.
Yeah.
Can you just go over how you
Yes.
got that way?
Yeah. Yeah. I'm waiting for these questions. So here is this is a triangle, and this is 90 degrees, and this is YL, and this is YB, and this is YA, and this is the distance A. This is the distance B, and this is the distance L. So simply you're taking the similarity of this small triangle with respect to the bigger triangle. Then you can tell YA on this side with respect to this side of that small triangle will be equal to the YL on the bigger triangle with respect to the size of that triangle. So using this one, you should be able to get this kind of relation quickly. Okay. Any other questions before I move on? If you, right now, for some of you still kind of taking notes, if you need a little bit more time, raise your hand before I erase it, okay? And the next one, this is the elastic beam. This is an elastic beam. So basically, you can find the equivalent spring constant. Okay, for example, this one will be this is a cantilever beam, so it has a template like 3EI and divided by L cubed, something like this one. So if we assign this is the E1, ELI, then you have this one. So if this is another ELI, then K2 will have the same pattern like this one. Okay, so basically, this is a one spring, this is a one spring, this is a third one, fourth one. There's a total of 4 springs connecting in such a case. And the loading, again, representing the loading applied is through here. We want to determine the spring equivalent spring constant, in terms of the degree of freedoms x here, okay? So we want to describe the spring, equivalent spring constant in terms of the degree of freedom x defined by this one. How can we proceed? I can tell you this is one example, the mixing, the combination of the springs in parallel and in series, they combined. And how to do it, you can give a try. This is one of our homework. For homework 1, I posted making that available this morning, so give a try. Okay. For the homework 1, there's a total 7 questions, and you can gradually work on that one. The due is Friday next week, and from this semester, all the homework due will be end of that day. For example, if the due day is Friday next week, the Friday is September 7th. So that due is the 11:59 p.m. So basically, end of that day, that's the due time. Okay. So think about this one, and again, this will be taking the free body diagram. My suggestion is taking the free body diagram from where the loading applied, and then tier-wise decomposing the whole system into the appropriate way. Okay, think about this one. This one been talking a lot, and so this is elastic bar, and so basically this is providing you more information. So for elastic bar, and so this is Young's modulus and cross-sectional area and length L, and we know this is a force here and deforming by delta. So delta equal to FL over EA. So we know the equivalent spring constant equal to F divided by delta, and equal to F divided by EA over L. Okay, so that's the spring constant for elastic bar. We've seen this one a couple of times. And for a torsional for a shaft, so like the transmission shaft of cars, okay, so that one we can approximate it. So in this case, if we apply a loading, for this case loading is equivalent to torque, okay, so let me use T. And for this case, we know we have an angle of the twist. So say this is at the free end, and the shaft has been twisted by this angle. Let me say this angle is here. Phi, okay, angle of the twist. So we know the P from mechanical material P equal to TL over GJ. And again, for this material properties, it has a rigidity modulus G, and J is the polar moment of inertia, and it has a length L. So we can calculate this. And equivalent spring constant are defined for a torsion is such that the force, which is torque, divided by angle. Okay, so basically this one is GJ over L. So that is the template of the formula. You can pick it up for obtaining the equivalent spring of the shaft. Okay, so that is the purpose of the Q page I provide here.